coming in. What's the temperature of the ocean during the summer? Any surfers in the house?
70 degrees Fahrenheit.
67 degrees Fahrenheit or something like that. So what happens is that this is hot, this is relatively cool compared to that. So thermal energy goes from hot to cold. And so that, cools the breeze. What about in the wintertime? Same, west coast of the US, winter. Ocean, right? Air, ocean, land. I mean, the same person can still get a suntan in the wintertime, right? And in general, the wind blows this way, right? But it's wintertime, so it's cold. Now, remember, I don't know if I said it, but the specific heat of water is relatively high. So it's not easy to raise the temperature of water or lower the temperature of water. So because of the high specific heat of water, in the wintertime, the temperature of the water here is maybe 57 degrees Fahrenheit. Just a 10-degree change or so. So now, this is cold, and this is now, hot compared to that. So now thermal energy goes like this. Right? And that heats up this wind. So you get a warm breeze. I mean, during the day, in the middle of the day, in the winter time, what is it like? 70 degrees, 75 degrees or so outside, and or let's say 70 degrees. And in the summertime, maybe 80 something. This is a special event going on right now this week. But the difference between the average temperature in the day, in the wintertime and the summertime, it's just like 10-15 degrees. Is really, maybe 15 degrees. It's not really that much. In the East Coast, what happens is, again, the wind blows from west to east, but it's going from land to water, right? And so then the winters are cold and the summers are hot, right? In fact, it is true that we have the desert over here, right? Usually when we get these heat waves and so on, it's because the wind is blowing the other way. It's bringing in the hot weather from Arizona and from those areas, right? Santa Ana winds, they call them. So then this doesn't contribute to helping with the weather. I'm saying helping because to me, I like it. I like the weather in Southern California, close to the beach. After having lived for so many years in cold winters and hot summers and humid, this is almost paradise to me. So, but when the wind blows the other way, then this effect over here gets messed up, and that's when it gets hot and so on. So there are two reasons why you have this relative, because it depends on it's a matter of opinion. Some people like it hot, some people like it cold. I have a friend who says, oh man, I love it, it's so hot. He just likes it. But the reason why you have this relatively good weather in Southern California, close to the beach, is because it's twofold. One is because of the direction of the wind on most days, right, from west to east. And number two, from over the water to the land. And number two, because of the relatively high value of the specific heat of water, so that these temperatures do not change much. So that then you can have, in the wintertime, thermal energy, pulled out of, going from the ocean to the wind, to the air, but reverse in the other case, because of the relatively high value of specific heat of water. In the East Coast, yeah, the water has there's the same relatively high value of specific heat, but the wind is blowing the other way, so it doesn't help. Okay, so that which is something else that came up, and I thought I'd say something about it. All right, so going back to chapter 18, right? So we have this ideal gas law. Oh, I guess I didn't say anything about these processes that I began to talk about last time. I don't know how self-explanatory these things are, but I'll talk about it anyway. So you can write the ideal gas law or the equation of state of an ideal gas as nRT or capital N K Boltzmann T. Right? Now, what if a gas is taken through some initial state to some final state? There's an initial state, there's a final state, right? I mean, there are so many different ways you can do this, right? So, I want to consider an ideal gas that's initially at some state described in, it's in some situation, and then something is going to happen to it so that its state is going to change. Its situation is going to change to a new state. And the transition from the initial state to the final state is a process. It's a transition, right? So what if the process is such that the volume is constant? In other words, like, you shut the doors in this room and we do something to the air in this room, and the volume of the room stays the same. Or maybe you have a flask or some container made of metal, and the metal doesn't really increase considerably in volume or decrease, so it's like the gas is trapped inside, and the volume stays the same, right? So constant volume, this is called, there are two words for this, isochoric, which I tend to use a lot, and the other one is isovolumetric. Iso means the same, volumetric, same volume, right? So isovolumetric is easy because it's iso, the same volume, volumetric. So I'll say isochoric so that you get used to that notation as well. Now, in a PV diagram, how do you represent that? In a PV diagram, so volume plotted on the horizontal axis, pressure plotted on the vertical axis. And these are equations of state, right? If I tell you the pressure and I tell you the volume, then we can use these equations to figure out the temperature if we know the number of moles or the total number of them. And the equation of state is just going to be described by a dot. So a dot on the PV diagram, this dot means, there's a specific value of the pressure, there's a specific volume of the volume, right? And then I can plug that in here and I can figure out the temperature, and so I can then learn about the state of the gas. So a dot represents the state, the situation that the gas is in. So maybe, for example, this one is, right, this is V initial, and this is P initial. Huh? If I give you the coordinates at that point would be like V naught, comma, P naught. Right? Now, if I take the gas, the ideal gas, through a process, and I forgot the T here, through a process where the volume is constant, that means that in this diagram, I need to move vertically. Suppose this is the initial state, and I take it to a new state so that it's going to be here. That's the final state. So it goes along that path, right? So I can apply the equation of state to the initial state, and I can apply it to the final state, right? So this over here, that's P final, same volume, right? So for this state over here, I can write P initial, V initial equals the number of moles R times T initial. And for this state over here, to describe that state, it will be the new pressure, the final pressure, times the new volume, which would be the same as the initial volume. As you can see, this is same as V final, right? Because I move vertically, right, in this diagram, equals nRT final. And if I write down those two equations and I divide them, for example, suppose I take P final, V final equals nRT final, and then P initial, V initial equals nRT initial. Notice that if I divide them, this n cancels that, and these two actually cancel because it's the same volume for this process, right? So therefore I get PF over P naught equals TF over T naught. So for every point, for every state along this process, if I take, there's a temperature here, T initial, there's a temperature there, T final, right? If I take this pressure and I divide by the temperature, I'm going to get the same value as if I take this pressure and I divide by that temperature. So this equation is not an equation of state. This equation applies to the process. So this is for the Isobaric process. And mind you, the temperatures here are not delta T's, so you must remember to use the absolute temperature in Kelvin, not in degrees Celsius. The way that I like to, instead of writing two equations of states and writing it like this, the way that I like to write it is like this. I have PV equals nRT. Notice that during this process, the volume is constant. So what I do is I write those parameters on the same side of the equation of the ideal gas law that remain constant. So for example, what if I write it like this? P over T equals nR over V, right? So, and we're talking about an enclosed gas, so you don't allow any gas to leak out or any gas to be added so that the number of moles remains the same, or the total number of molecules remains the same, right? So, if during that process I have the same number of moles throughout, in the gas, this is a constant, and the volume is a constant, then all of this is a constant. And therefore, this ratio has to be true everywhere in that process. So I can write P final over T final, it has to be equal to P initial over T initial. And if there's another one over here, like, at that point, the temperature is T3, and the pressure there is P3, then this also means that this will be equal to P3 over T3. So this vertical line represents what's called an isobiometric process or isobaric process. And all it does is it relates the initial pressure to the final pressure and to the initial and final temperatures. The volumes are the same. What if the gas is taken through a process that changes the state of the gas from some initial state to some final state, and during that process you are careful to keep the pressure the same? That's called an isobaric process. So what happens if you have an isobaric process? And just to do it, if you want to do it quickly, again, what I do is I lump together on the same side of the equation those quantities that remain the same. So if the pressure remains constant, I just write it like this. P over nR equals, and then the quantities that change, I'll put them on the same side. So if this is a constant, right, then this has to be a constant. So I'm going to get T initial over V initial equals T final over V final. Or I can just reverse it, right? Or you can do it like this. You can write down, you can consider an isobaric process. So I'll just make this number 2. And how would you represent that on a PV diagram if the pressure is constant, right? Well, suppose the initial state is this, and it's taken to a final state here. So that way the pressure will remain constant. So everywhere on all of these states over here, the pressure is the same. So you could write down an equation of state, this would be like V initial. This here would be V final. The temperature here will be T initial. And the temperature there will be T final. The pressure initial and P final will be the same, right? Sometimes I use a 0 to mean initial, and sometimes I use I. So I don't know, maybe that says something about my personality, but 0, I tend to use 0, but more than I, but. Okay, so I can write the equation of state for that state. That would be P initial, V initial equals nRT initial. And I can write the equation of state for that state. That would be P final over V final equals nRT final. And then I divide them. And then this pressure is going to cancel that because it's the same, they're the same pressure, right? The pressure is constant. This N cancels that, this R cancels that, and I get V initial over V final equals T initial over T final. And if I cross multiply this, right, I can write it into this form. I can write it as V initial over T initial equals V final over T final. So this equation applies to all the states along this isobaric process. Yes? Isobaric. So that's what that is. I mean, this is relatively simple. And for the constant temperature is called an isothermal process. Why does the curve on a PV diagram look like this for an isothermal process?
Because pressure and volume is changing.
And why not something different than that? Yes, both pressure and volume will be changing, that is correct. Well, why does it not look like this, for example? Or maybe like that? Or maybe like that? I don't have a temperature axis, so why does it look like that?
I can't say for why it's curved, but it's negatively sloped because as volume would increase, pressure decreases, and then vice versa, as pressure increases, volume decreases.
Yes. So why not this? So if I ask you to do this graph, y is 3 over x. What would that look like?
Curve approaching.
Is that a line? Is the slope 3? No. It's something like this, right? Well, the ideal gas law is PV equals nRT. If I solve for the pressure, it's nRT over V. Now, if the process is isothermal, all of that is a constant. So now this constant is like the number 3 over there. So the process has to look like this. Like that curve. Right? And it means that if the temperature here is, let's say that's the initial state, and this is the final state, right? That means that if the temperature here is 300 Kelvin, here it's 300 Kelvin. Everywhere on this point is on this curve is 300 Kelvin. 300 Kelvin will be the final temperature, right? If the temperature is 400 Kelvin, is it here? Or would 400 Kelvin be here? What do you think? The green or the red curve, if the temperature is constant during the process, but not at 300 Kelvin, but higher temperature. You think it'd be the green curve or the red curve? The green. So this would be like a 400 Kelvin. This would be, I don't know, 200 and whatever. I'll just say 200 Kelvin if you keep it as a gas, right? So the higher the temperature, the further away this is from the origin. So how do you find the relationship between pressure and volume? Both of them change during an isothermal process. Well, P times V is a constant. So this is a constant, right? So this is a constant. So you just get the P initial, V initial equals P final, V final for this curve, right? So the isothermal process is described like this. And P initial, V initial equals P final, V final. Clear? Okay, this one here, Boltzmann actually wrote down this theory, and some other people contributed as well. I like to think of, the way that I like to say this is that when you consider the ideal gas law, or the equation of state of an ideal gas, right, you talk about the pressure, right? It's the pressure exerted not by one molecule or atom, it's the pressure exerted by the whole gas, right? So it's a macroscopic variable. It refers to the whole thing, macroscopic, as opposed to, when you say micro, here, you mean like at the atomic level, when you're looking at the individual atoms or molecules. So the volume is the one occupied by the entire gas. That's a macroscopic variable. The temperature is the one, you don't talk about the temperature of one atom or the temperature of one molecule, it's the temperature of the whole gas, right? So it's a macroscopic variable. Yet, this lowercase m over here, and n is the total number of them, it refers to the macroscopic gas. But this m over here is the mass of one atom. Like when I drew my picture at the beginning today, and that's the mass of one atom or one molecule. So now that's a microscopic variable. It has to do with, at the atomic level. And then this V over here is, actually I forgot oh no, it's good. I wrote average. So this is the average of the squares of the speeds. And that has to do with the speed of the atoms. So it's a microscopic variable. So what Boltzmann did is he was able to make connections, or to write down a relationship between the macroscopic variables, parameters that are used to describe the state of the gas, and some of the microscopic parameters that are used to describe the atoms or the molecules, right? So he wrote this expression, right? So I think it's derived in the book, and we can look at it, but I don't want to spend time doing that. Now, let me show you something that comes out of that expression. By the way, you might be wondering, why did he not cancel this 2 with this 2? The reason why I did that is because I wanted you to see that. What comes to mind when you see that expression? 1/2 times 1/2 the mass on the speed squared. Right away, what comes to mind?
Kinetic energy.
Kinetic energy, right? So I wanted to leave the 2 in there, but then I had to put the 2 over there. The 3 over here, where does the 3 come from? I mean, I haven't done the derivation, but the 3 over here comes from the fact that the atoms and molecules move in 3 dimensions. Like in this room, they're moving right and left, up and down, or in out. So the 3 has to do with the motion of the atoms in 3 dimensions, right? That's where that comes from. And then this is the total number of them, of atoms or molecules that makes up the system, the gas. This is the total volume occupied by the gas. This is the pressure exerted by the gas. And, this expression relates you can think of this sort of like an average kinetic energy of each molecule. The 1/2 mv squared over there, is like the average kinetic energy of each one of them. Now, not all of them have the same kinetic energy. Not all the atoms or molecules of air in this room are moving at the same speed. Like if we were to freeze, not freeze, but stop time, and we said, okay, this air molecule, like this oxygen molecule, this nitrogen molecule, and so on, and if we were to track the speeds of all the molecules that makes up the air, they're not all going to have the same speed. But if you take the speed of this one and you square it, and you take the speed of this other molecule and you square it, and you take the speed of this other molecule and you square it, and you take the speed of this other molecule and you square it, and then you take the average of the squares of the speeds, that's what this quantity is. So, but also we have this equation of state, right? PV equals N K Boltzmann T, right? Or we can write in terms of moles, but I just rather, since we have a capital N over here, I'll just write it like that. So notice that I can write this equation of state as N over V times K Boltzmann T. But also, Boltzmann wrote this expression that P equals, so I'm going to write N over V separately. And what else? Then it's 2/3 of that quantity, right? So then we have 2/3 of 1/2 mv squared average, right? So if I compare this to this P is this P, this N over V is this N over V, therefore this quantity has to be equal to this quantity, right? And I don't want to cancel the 1/2 because I want to call that term the average kinetic energy. So I want to call this will be like, I can write this as N over V, which will cancel, and then the 2/3, and then like an average kinetic energy of each molecule. Of each molecule. I want to emphasize that because this mass over here is of each one of them. So then that means that that has to be this. Right? So KT, K Boltzmann T has to be 2/3 of the average kinetic energy of each molecule. And if I solve for the average kinetic energy of each molecule, therefore I get 3/2 K Boltzmann T. And that's a very famous expression. This is what people use to say that, this is one way, in fact, of defining the temperature of a gas, right? How do you define the temperature at which it's at? It's like a measure of the average. And this is translational kinetic energy of the atoms or molecules that makes up the gas. The faster they move, on average, the hotter the gas. You cool down the gas, on average, you're going to move down more slowly. Yes? And if you combine that expression with this other one, it also makes some sense, right? Because what this expression is saying at the top is that the pressure in the gas, right? It's also the pressure at which the gas, that the gas exerts on the walls of the container. So if on average the molecules are moving faster, they're going to hit harder. And they're going I don't want to, I think there's a class next door, but so if the molecules move faster on average, they're going to hit the walls harder. And if you average the force over 1 meter squared, that's the pressure. So the faster they move, the bigger is going to be the pressure that the gas exerts. And the faster they move, the greater the average kinetic energy of the molecules, right? So the greater the pressure, the greater the average kinetic energy of the molecules. Again, the 3 here comes from the motion of the atoms in 3 dimensions, right? In space, right? They can move in 3 dimensions. So that means that for every dimension, the average kinetic energy of each molecule is 1/2 kT, 1/2 k Boltzmann constant times T. Now, sometimes you see the expression written like this. Okay, so let's go back to that expression above. This one. Let's go back to that expression up there. So the 3/2 kT, right? That's this one. And, that's the average kinetic energy of each molecule. So I'm going to write it like this. What is it? 1/2 m, that's the mass of each molecule, right? And then this is the average squared, right? Is equal to 3/2 k Boltzmann T. Now, notice this is V squared, average. Suppose I solve for V. If I solve for V, this 2 is going to cancel this 2, and then I have V squared average is equal to 3k Boltzmann T divided by the mass of each molecule, right? But this is V squared. If I want the V in meters per second, then I have to take the square root of that, right? And that would be the square root of 3k Boltzmann T over m. So this is a speed over here. But what is it? It's the square root of the average of the squares. Go from the outside towards the inside. It's the square root of the average of the square. So it's called RMS,